Okay, so long time no see because of the weather. So we're gonna have to move to the lecture 2, and we will review the biochemistry information, a couple of cycles. This part we talk more detail in the biochemistry class, and we also talk in the microbiology class. When we mention about these chemistry material and also the cycles, we also going to do a preview what we will talk during the semester when the class goes on. So we're going to have to do here is a overview of biochemical, I would just say cycles. So first of all, we talked about electron arrangement, and we talk about those atoms, how they arrange. So when we talk about the biochemical cycles, there is an overall picture can describe that. So all the chemicals, we have an electron donor and an electron acceptor. So if the electron donor is organic chemical, and the electron acceptor is also organic chemical, and this reaction we call fermentation. And we will be mentioning fermentation when we talk about the manufacturing of vinegar, to talk about detail. If the electron donor is organic chemical, and the electron acceptor is inorganic chemical, this is we call respiration. And obviously the respiration has two different types, which is aerobic and anaerobic. So aerobic, the final electron acceptor is oxygen, and anaerobic is other inorganic chemical, but not oxygen. So I will just say other than oxygen. Okay, so today we will do a review. We'll focus talk about is aerobic respiration, how many ATPs generate, and what is ATP, how the ATP produced. We talk about chemistry, we talk about structure. Okay, so that's an overview picture. Now the second, we want to talk about these cycles. So we also want to have an overview picture here. So the big picture will be we have a glucose. Okay, then glucose, we're going through this branch reaction. Will generate a very important chemical that is called pyruvate. And we call it metabolic intermediate products. Then the pyruvate will obviously go acetyl-CoA, and then acetyl-CoA will go this cycle. And this cycle, we call it a TCA cycle, tricarboxylic acid cycle. We call it a Krebs cycle, named by the scientist name. We also call it a citric acid cycle. So we're going to talk a detail of the cycle, talk about all the structure of the chemicals, and something we will mention. Now the pyruvate, in the absence of oxygen, they could go this direction. That will happen is fermentation. So we just talk about it. Now the fermentation also have two categories, which is homo fermentation, generate only lactic acid, and hetero fermentation will generate other chemicals other than acid. For example, alcohol. Now the alcohol, if they're going through a second fermentation, then finally will become a vinegar. And this we will talk later on. So, the second lecture is basically still review, but we will talk more in detail. Okay, so let's talk about this process. Glucose go to pyruvates, the name called glycolysis. So let's do that. So the first one, glycolysis. Glycolysis. When we talk about these chemicals, we need to know the structure. First of all, we need to know the name, then we need to know the structure. So what's the structure of glucose? So glucose looks like this. Okay, it's a 6-carbon ring with the oxygen in the middle. Then it's composed by HOH, HOH. They are going the upside down direction. So CH2OH. So I think this is the basic you need to know. This is a glucose. We will later on talk about like the D configuration, L configuration, and we also will talk about the glucose have 3 different express. This is we call it Fischer configuration. Then there could be the open ring forming writing form, or could be chair configuration. So we will talk later on the details. So that is glucose. Glucose, the first reaction, we need to add a phosphates, so it become glucose 6-phosphates. So that's we just draw real quick. Okay, H, OH, H, OH, OH, H, OH, H, H, CH2O, and you have a phosphates right there. Now here we can talk where this phosphate goes. Obviously is ATP hydrolyzed become ADP and release a phosphate, and then the phosphate goes here. So this is a 1 is on a 6th position. So this is 1, 2, 3, 4, 5, and 6. So we call it a glucose 6-phosphate. And I use P to represent phosphate. Now what is the enzyme for this one? You learned in your chemistry class called hexokinase. And I will say that's part of that. Hexokinase is usually for animals, human beings, and plant cells, so it's for eukaryotes. I'm teaching microbiology and also a microbiologist. So I want to tell you for bacteria, they are not rely on hexokinase. They are going through a more complicated procedure. We call it a group translocation. And we talk about this relay on phosphoenolpyruvates. So we'll get to that. So that's for bacteria. So glucose 6-phosphates, the second one. Then, going through a process which is basically didn't change anything but the structure changed. So the chemical components did not change. CH2O phosphate. So we have H, OH, OH, H. This is H, CH2OH. Very important, this is H, is not OH. So what is that? This become another different sugar is fructose 6-phosphate. So fructose, when you see the words fruct, F-R-U, looks like a fruit. So it's coming from lots of the produce. They generate the fructose. Not very sweet. We'll talk about that. The sweetest one is sucrose. It's not very sweet. That's fructose. So fructose 6-phosphates. And this is glucose 6-phosphates. So it doesn't have anything change, only the configuration change. So this process we call it isomerization. So the enzyme called isomerase. Okay, now what happened? When you see these things, there is a phosphates right here. Here there's no phosphates. Obviously, you're going to keep the balance for the chemicals. So you need to add another phosphates there. So the next step will become a very special, so I'm going to use this one. You will see is CH2O phosphates, H, OH, OH, H, goes H, then CH2O phosphates. So you have two phosphates there. Their name called fructose 1,6-biphosphates. So what is the enzyme for that one? This is just a kinase, okay? Fructose 6-phosphates kinase. But what happened? What's the difference? Fructose 6-phosphates, only one phosphate. Here you have two phosphates. Now where they comes from? So it comes from ATP. So they happen again is ATP, hydrolyzed become ADP, and donates the phosphate. So at this stage, we are talking about this small section. This small section, we hydrolyzed two ATPs. I won't say two ATPs, we'll say two locations happen is ATP hydrolyzed and generates the phosphates. So this one we call it investment stage. It's like you're buying a stock and you need to put some money into the market and try to get money later. Okay, then we go to this branch reaction. And I will write chemical on one side and name on the other side. So fructose 6-phosphates. Fructose 6-phosphates will go to a branch which is create CHO, CHOH, CH2O phosphate. This is called glyceraldehyde 3-phosphate. So here there is a phosphate. If there is no phosphates, what it looks like will be CHO, CHOH, CH2OH. This is a simplest sugar. We will talk when we go to the carbohydrate section. It is aldose. So why we say it's aldose? Because on the top, this is this structure. It's aldehyde. And in opposite to that, we have a ketose. That's the simplest sugar, 3-carbon. Okay, so glyceraldehyde is 3-phosphates. Glyceraldehyde 3-phosphates in some of the textbook, they are going through those transition steps. Will become CHO, CH, 2O phosphate, so dihydroxyacetylphosphate. Dihydroacetone phosphate. Dihydroxyacetone phosphate. Hydroxyacetone phosphates. That's a transition step. So glyceraldehyde 3-phosphates. So we go down. Has a very important chemical we'll generate is COOH. COO phosphates. We have CHOH, CH2O phosphates. This is 2 phosphates, so 1,3-biphosphoglyscerate. This is a very important chemical. How this happens, there is a phosphates goes here to donate that. At the same time, happened is NAD reduced to NADH2. NAD, we know that, same as FAD, is an electron carrier. And when they accept two protons, become NADH2, so it's reduced. And we will learn about that later. This process will generate 3 ATPs or 2.5 ATPs, depends on whether you calculate the ratio of the phosphate and the oxygen. So 1,3-biphosphoglycerate. What's the enzyme for that? Dehydrogenase. It's a very important enzyme. Okay. So 1,3-biphosphoglycerate generate. Goes next one. So 1,3-biphosphor. We don't like that much. We take it out. CHOH, CH2, O. We still have a phosphates right here. So 3-phosphoglycerate. Then become 3-phosphoglycerate. So where is that phosphate goes? Remember, we have an investment period right here. We put the money into the stock market, but we haven't get anything yet. So here is ADP with phosphates, then becomes ATP. That's an ATP created. The first place. I will say the second place. Okay, so 3-phosphoglycerate. The next one is transition the place. That's become COOH, CHO. The phosphates moves up. Then go here, CH2OH. That's 2-phosphoglycerate. Because the position from the carbon number 3 go to the carbon number 2, so 2-phosphoglycerate. This is happened. Doesn't have anything. It's only moved the P phosphate from the carbon number 3 to carbon number 2. So that's the name of the enzyme. Is just a kinase. But the process is actually, it looks like an isomerization. Okay, the same chemical compounds, the structure looks like the different, but chemical compounds are the same. So 2-phosphoglycerate. 2-phosphoglycerate. I go this way. Once you have a 2-phosphoglycerate, you see notice the chemical right here, the chemical right here. Then we'll generate a very important one. COP and double bonds CH2. And this is gone. A water molecule of the water is gone. This process needs an enzyme called enolase. Enolase. Later on we will learn. The process is called enolization. What is enolization? Talk about is basically lose water from the molecular standpoint. When we talk about Maillard reaction, we will mention 1,2 enolization and 2,3 enolization. So here we have to review, is there lose water? Okay, so what is this guy? Phosphoenolpyruvate. That is phosphoenolpyruvate. Acronym we write PEP. And I said for bacteria, this is very important. For bacteria, they will go back all the way to here to contribute the first step through group translocation, let glucose become glucose 6-phosphates. There is a slides for that in the other class, in my other class, and talk about details, and then we're gonna just skip that. Okay, then this guy goes here. What happened? COOH, CO, CH3, this is pyruvate. So where is this guy goes? Obviously is ADP with these phosphates, so generate ATP. Okay? So that is a procedure. What we happened here is going to pyruvate. It's intermediate metabolic chemicals. We're going to go back to talk about the calculation of the ATP. Okay, so let's continue to talk pyruvate. So glycolysis is finished. Then we go to citric acid cycle. Okay. Citric acid cycle, there is a transition step. COOH, the pyruvate. We are going through a transition step. Let me just draw a little bit top. Okay. Draw like this. COH, CH3. Going through transition step, lose carbon dioxide, accompanied with NAD, reduced to NADH2. Needs other chemical helping, which is acyl-CoA, so become SCOA. That's acyl-CoA. Coenzyme A. This is a very long, complicated chemical. When we learn in the chemistry class, or biochemistry class, is already been concise one. Okay, acyl-CoA. Acyl-CoA, we are going to, next chemical, I will say it is a very important one, citric acid. Okay, what does citric acid looks like? COCH2, COH, COOH, CH2, and COOH, citric acid. So we already said it's a citric acid cycle. So you need to know the structure of citric acids. There is something we want to mention related to that. Citric acid is an antimicrobial. So in the later lectures, we will talk about the mechanism of the citric acid to killing the bacteria. Second, we also in the fresh produce industry, when they prepare in the chlorine water, and we'll talk about the chlorine water when we go to the water section, we have to adjust the pH. So we're using citric acid to adjust the pH. The pH for a pure chlorine is about like 10, the alkaline environments, and we need to let the pH go down to 6.8, so we add citric acids. So those are the things we'll later on talk about. Okay. Citric acid, the next one. That's a little bit different in different classes. What you guys learn is called cis-asconic acid, or cis-asconate. This one, I skip it in my class. I don't talk because it's not in the bacteria. So citric acid directly become isocitric acids. Isocitric acids is hydroxy bonds is just removing. So become COOH, CH2, CH, COOH. We go here COH, H, and COOH. So that is Isocitric acid. Isomerization. Okay, the next one is important. The next step will happen is losing carbon dioxide accompanied with NAD reduced to NADH2, create another important chemical, which is COOH, CH2, CH2, that's called alpha ketoglutarate. So we just want to make sure this is correct. It's alpha ketoglutarate. There is a ketone here. So alpha ketoglutarate. Okay, alpha ketoglutarate. A little flat. When you see the structure like that, this is here is easy to go away. So they lost carbon dioxide. Also happened NAD reduced to NADH2, and adding coenzyme A, so become COOH, CH2, CH2, this guy, SCOA. So what's the name for that one? Succinyl-CoA. Okay, then you go flat right here. This is easy to go. This is very easy to take it out. Okay, then become a very symmetric structure, COH, CH2, and COOH. What is that? Succinate. That is succinate. It's an important one right here. And this happened is GDP generate GTP. And when we talk about the energy creation, from the energy standpoint is GTP same as ATP. And we are going to talk about the structure later on, okay? Very similar. So that's succinate. When you have a succinate that comes here, you see these two H2 right in the middle. That is easy to lose. So what happened? Then become a chemical, yes, COOH, CH, double bond, CH, COOH. That's fumarate. Fumarate. Now where is those H go? Where is those proton go? So proton have to go some places. What happened here is FAD reduced to FADH2. So NAD, we call nicotinic adenine dinucleotides, that's fulving adenine dinucleotides, is another electron carrier, so they become fumarate. So once the fumarate comes out, double bonds right in the middle, we try to let it be saturated, because it's an unsaturated status. So the next one, what happened? We need to put them back. OH, CH, okay, OH, then CH2, and COOH. This stage, they need water. They need water coming. Okay, so this has become a malate. Very similar to malic acids. Malic acids is used or created during the beer brewing process. It's a malic acids together with the hops. So the beer, when you taste it, a little bit bitter. But more importantly is the hops. But the malic acids is there. It is also antimicrobials. So last one, we almost done. You see here, something gonna go, because it's not stable in the middle. The chemical person will tell you about these energy bonds. The kJ per mole, then they will tell you it's not stable, they're gonna go. We're not gonna get to those, okay? Become COH, CH, this sorry, this up is keton. So CH2, then COOH. That is called oxaloacetate. Oxaloacetate. And this goes here. Okay. Now, what happened right there? It also happened that there is a NAD reduced to NADH2. Happened right there. Okay, so this is the whole name is citric acid. So we finished. Okay, we finished to talk about here. Then we want to do the calculation of the ATP. So that's calculation of ATPs. Okay, we want to, then we go back to talk about the ATPs. Calculation of the ATPs, we need to find where the ATP is used, where the ATP is generated. So let's talk about this step first. At the beginning, this investment stage right here, you see there is 2 ATP are hydrolyzed. So this is minus 2 ATPs. It's fixed. Then, from here to here is pyruvate generate. This is created ATP. And how many ATPs they created? So we need to circle the places where they created it. Right here, 1,3-biphosphoglycerate becomes 3-phosphoglycerate. And finally right here, which is phosphoenolpyruvate become pyruvate. So how many ATPs they generate? Is 2 ATPs. However, this is a branch reaction. So let's do this. 2 minus ATPs here. So 2 ATP generate here, and 2 ATPs generate here. Okay, so this has to multiply by 2. That's 4 ATPs. So minus 2 plus 4 ATPs equals 2 ATPs. That is a lot of the textbook at the end saying glycolysis have 2 ATP generated. That's kind of confusing people. Because when they say 2 ATPs generated through glycolysis process, they think the glycolysis is an individual closed cycle. They did not calculate as part of the aerobic respiration. So if glycolysis is part of the aerobic respiration, then this guy here needs to be counted. So how we do that? NAD reduced to NADH2. In the old time, we say 3 ATPs generated. In the new textbook, after 2010, they consideration the phosphate oxygen ratio. Therefore, this becomes 2.5 ATPs. And then there is another similar chemical, which is FAD. We mentioned the following adenine dinucleotides. Then become FADH2. In the old time, that is 2 ATP generate. And then if you think about oxygen phosphate ratio, that is 1.5 ATPs. And I usually still use the old rules because it's easy to do the calculation. 0.5 is always confusing. So what happened right here? This alone is generated how many ATP? It's 3 ATP right here. But 3 ATP has to be multiplied by 2. Is that right? So This is right here is 3 ATPs multiplied by 2 is equals 6 ATPs. So if you write here, that is 3 ATPs here, 3 ATPs here. So how many total from glucose to pyruvate? If the glycolysis is part of the aerobic respiration. If you add up these together, minus 2, add 3, add 3, add 2, add 2, that equals 8 ATPs. Okay, now we're going to talk about right here, encoding the transition state. Then we're going to have to find where the NAD reduced to NADH2 happens. It's place, second, third. So how many generated? That's 3 ATPs multiplied by 3. And there is one place happened, FAD, oh sorry, I forgot one. There's the right one here. So 1, 2, 3, 4. So that's 3 ATPs multiplied by 4. And you need a plus, which is FAD reduced to FADH2. Okay? So there's one right here. You plus 2 ATPs. And do not forget, there is a GTP generated. That's equivalent to ATP. So you need to add 1 ATPs. So how many ATP generated? Total is 50 ATPs. And remember, the one branch has one cycle, another branch has another cycle. So the Krebs cycle happened twice. So this has to be multiplied by 2, therefore equals 30 ATPs. And then you add up together, here is 8, here is 8, here is 30, so the total is 8 add 30 equals 38 ATPs. That is a calculation. 38 ATPs is for the bacteria, which is prokaryotes. Eukaryotes is a little bit complicated because they have to pass in the mitochondrial barrier, so they usually will use 2 ATPs. So that's the easiest way to do is just 38 minus 2 ATPs, then equals 36 ATPs for plant, animals, and human beings, just going through the complete aerobic respiration. I think this is a very good way to review all these chemicals, calculate the ATPs. This is usually is an open book question for the exams. And if you're a PhD student, for the qualified exam, if your qualified exam is not writing a grant proposal, then I usually will ask you to do the calculation because it's a very good review of the biochemistry. Now we're going to go back to talk about the ATPs. Okay. So we haven't talked about the structure of the ATPs, so we want to talk about the ATP, what it looks like. This is energy currency, everybody knows. 3 prime, that's called 3 prime adenine or adenosine triphosphates. So what is the structure looks like? Using the review of the structure, we also can review the DNA structure and RNA structure. So what it looks like? So adenine, that's it, the adenine, is composed by 2, so how is it, ring carbons. There is a 6 carbon and a 5 carbon. And they become the NH2 on the top, N, then they like this. And here is N, this is N, this is H, and they go this way. Okay? So that's adenine. And the adenine is connected by a 5 carbon sugar It's going through pentose phosphates. And this will be H, OH, H, OH. It goes through H, so it goes through CH2. Okay, going through CH2, I have to delete this. So CH2 goes here, yes, O phosphates, O phosphates, phosphates. And this is, we say, high energy bonds. So that is the structure of the ATP. This is also could be explanation of the DNA, what it looks like, and the RNA, what it looks like. This is the base. So when you study the DNA, RNA structure, the basic one. That's carbon, the 5-carbon sugar, the ribose we call it. Okay, ribose right here. So this is 1 prime, 2 prime, 3 prime, 4 prime, and 5 prime. In the 1 prime, they will be connected to a base. Then this is we call the nucleates. The base of FDST is ATGC. So this is adenine. Then we have a thymine, guanine, and cytosine. Then A and G we call it a purine, T and C we call it a pyrimidine. And then goes here, if this oxygen is gone, we call it a deoxynucleotides. Then what we're missing here is obviously is a phosphates right here. Okay, so that is ATP. Now, we said during the citric acid cycle, we have GDP become GTP. So GTP is equivalent to ATP. Therefore, what is GTP looks like? The only difference is this base is different. So what are the difference between the base? It's exactly, lots of the places exactly the same. The base the difference. Here are the same, 6 carbon. Exactly the same for the 5 carbon area, H, NH. And this is gone when they connect it to ribose. Okay, the difference is right here. This should be NH2. Let me double check. No problem. Talk too much, I forgot. Yes, it's correct. Guanine looks like that. So that's guanine. That is guanine. Okay. So then we left these T and C. What does the T looks like? That's thymine. Thymine only have 1 6 carbon. Looks like it. That's thymine. TTP also could become an energy currency, but we just don't talk about that. Okay, so that's thymine. If thymine, we label them 1, 2, 3, 4, 5, and 6 carbon. If this 6 carbon is gone, okay, look at this, exactly the same. Right here. NH, go. So at 6 carbon, instead of you have a methyl group, which is CH3, we replace with H. Then what is that? That is uracil. So when you remember that, it's very simple. The thymine and the uracil, the difference is at 6 carbon, which is at an unimportant place, a methyl group is replaced with a proton or with H. That becomes uracil. Then what the last one we are missing? We did talk about cytosine here. So what is cytosine? You go here. When you have this, it's the same. The only difference is this is replaced with NH2. And here is O. And this is CH3. This is H. And then you have NH, N, and N. So then you go here. Then you go here. That's all. Then that is cytosine. So when you study it here, you can know all these structure, what it looks like. The ATP, GTP. That's from a structural point. That's why the GDP becomes GTP is equivalent to ATP. Okay, now we have other things we can talk. Is how the ATP will be generated during the biochemical cycles. There are two ways the ADP becomes ATP. You learned in your class, we can just, a different class, we can just review. One is called oxidative phosphorylation. Then verse, the second one is substrate level phosphorylation. So we always have a question sometimes in the biochemistry class. What is oxidative phosphorylation? What is substrate level phosphorylation? Lots of the students is easily understanding the oxidative phosphorylation because you know it's related to the electron transport chain. So we can do a brief review. So the electron transport chain looks like we have NAD, H2, then we have FAD, then we